Hello everybody, welcome back to another geometry lesson. Today we are going to be talking about section 5.5. Now with this section, just like in section 5.3, we're going to find more ways to prove that two triangles are congruent. I'm going to call these ways our success conditions. When I say that, I mean the different things or the different pieces we need to show that two triangles are congruent. One of our success conditions is all sides and all angles being congruent to each other. That's where we said that two triangles are congruent if all corresponding parts are congruent. That's something that we used very early on in this unit. All corresponding parts being congruent. Last section, we learned that if a side, an included angle, and another side were all congruent, then the two triangles are congruent. We are now going to add two more conditions, and the easiest of these is the side-side-side congruence theorem. This one basically says if all the sides of both triangles are congruent, the two triangles are congruent. So, for instance, let's say I have two triangles, both of which looking like acute scalene triangles, like this. And I know that each side has a congruent counterpart. If I know that all the sides of one triangle are congruent to all the sides of another triangle, it means they're going to be congruent triangles. They're basically going to be the same. That is the side-side-side congruence theorem. In words, if all sides of one triangle are congruent to all sides of another, then the triangles are congruent. If all sides of one triangle are congruent to all sides of another, then the triangles are congruent. Perfect. So let's do a proof that involves this. This is going to be a super short proof. Example 1 down here tells us the following information. KL is congruent to NL. KM is congruent to NM. So what we have in our given here is that two pairs of sides are already congruent. KL and NL, KM and NM. These are our givens. So all we need to show is that the third side in each triangle is congruent. Well, on the left triangle, the third side is LM. The third side on this triangle is LM. And what do we know about that side when it's the same, when we're talking about the same side? Well, it's congruent to itself. LM is congruent to itself because of what? If you said the reflexive property of congruence, you're spot on. Some reasons pop up more frequently in proofs than others. In Unit 3, we were talking all about the transitive property. In Unit 5, the property that's going to show up quite a bit more than usual is this reflexive property. Always look to see if your triangles share a side, because it's likely that the reflexive property will be popping up. So if we know that we have the red sides congruent, the blue sides congruent, and the purple sides congruent, that means all three sides of both triangles are congruent. We can say that triangle KLM is congruent to triangle NLM, just like it says in our proof statement, because of side, side, side congruence theorem. Nice! This is a quick proof. Before we talk about this last theorem, I'd like us to flip over to the back side. Take a look at example 2. We've practiced this at this point a little bit, but I want you to see what you can do. I want you to pause the video, see if you can find example 2's proof all on your own. And I'll give you a hint. It's probably going to use side-side-side congruence theorem. Try this out, see what you can do, and come back to the video in a couple minutes. Let's pause here. All right. Hopefully you had a chance to pause and try out this proof. Again, the only way we're going to get better is by trying these out yourself. So let's check what we did. First things first, let's talk about our givens. So line segment PQ is congruent to line segment RQ. That just means that this long side of the triangle and this long side of the triangle are congruent. But we're also told that line segment QS bisects line segment PR. What does that mean? Well, it means that this vertical line here from Q to S cuts the bottom line in half. So what do we know about bisections? If it cuts the line in half, then each half is congruent. We can say that line segment PS is congruent to line segment RS. And again, that's just because it's cut in half. That's what bisection means. It's the definition of bisection. Note, the only reason why I wrote it this way, PS and RS, instead of like SP and SR, is because I'm looking at my proof statement and how they wrote it out there. It's not a requirement, but it's a recommendation. So if that bisects it, we just need one more side. We just need to show that QS in this left triangle is congruent to, well, QS in this right triangle. Hang on a minute, that's the same line. Anytime you have the same line shared by both triangles, it's congruent to itself. We can say that QS is congruent to itself due to the reflexive property of congruence. And lo and behold, we have all three sides being congruent. So, if all three sides of one triangle are congruent to all three sides of another, then by side-side-side congruence theorem, the two triangles are congruent. Very nice. Note that with this problem here, I could have given you slightly different information, and it would have changed the entire problem. In this unit, there are many different ways to show that a triangle is congruent. We've already learned 3 of them. Let's pretend, for instance, that I told you the following information. I still gave you that PQ is congruent to RQ, so I still told you that these two sides are the same. But instead of saying that QS bisects PR, what if I said that QS bisects angle Q? All I did was I just changed one piece of information slightly, and it completely changes how we can approach this proof. Well, if QS bisects angle Q, then that means that the angle itself is cut in half. It means that this left side of the angle is congruent to this right side of the angle. And once again, we can show that QS is congruent to itself. All of a sudden, we're not dealing with side-side-side congruence. We're dealing with side-angle-side, just like in 5.3. So keep your eyes open. You might be able to prove two triangles are congruent in different ways. keep in mind the information that you're given. All right. Let's talk about this very last theorem, the hypotenuse leg, or HL congruence theorem. Side-side-side congruence theorem was nice, but it still required 3 pieces of information. We had to show that all 3 sides were congruent to each other. Hypotenuse leg is a shorter way of proving it, but it requires a bit more setup. The hypotenuse, if you recall, is the name we give to the longest side of not just any triangle, but to specifically a right triangle. So this theorem will only work if you have a right triangle. But it basically says this: if the hypotenuse on both triangles are congruent, and one of the legs on each hypotenuse, or on each right triangle are congruent, then the 2 triangles are congruent. Only works on right triangles, but it certainly saves some time, right? Let's write this down. The hypotenuse leg theorem says if the hypotenuse and a leg of one right triangle so it has to be right triangle, are congruent to another's right triangle, so if the hypotenuse and a leg of one right triangle are congruent to another right triangle's hypotenuse and leg, then the triangles are congruent. This is great because if we already know that something is a right triangle, we can just say, oh, we can find the hypotenuses are the same, we can find out the leg is the same, we're good to go. The key to this type of problem is finding out that something is a right triangle. So, in these blanks, the hypotenuse leg congruence theorem is different from the others in that it requires a right triangle in order to work. Recall the hypotenuse of the right triangle is the longest length, so always look for the longest one, and that's your hypotenuse, and a leg is just another one of the sides. It is so super important to note that this type of congruence does not work in any other circumstance unless it is a right triangle. We have sometimes called this idea side-side angle congruence, and it does not work unless it's a right triangle. Let's say you've got a triangle with a longest length of 5 and a smaller length here of 2. And another one with a longest length of 5 and a smaller length of 2 like this. These are 2 very different triangles when we complete the third side. One of them is obtuse, one of them is acute. These are not congruent triangles. But you might be convinced that they are the same triangles because, oh, 2 of the sides are the same. It doesn't work unless it's a right triangle. So be very careful. All right. Let's take a look at the final proof for today. In this proof, we see that we have 2 triangles that are sort of overlapping. Here's a hint. When there are too many parts to keep track of in a diagram, redraw the diagram separating the 2 triangles we're trying to prove. So we're trying to prove that WYZ, which is this triangle in the diagram, the one that goes from W down to Y over to Z, is congruent to x, z, y. There's z, there's y, there's x. Any information that's in our given, we want to replicate onto our diagram here and the main diagram to help us. So the first thing we are told is that wy is congruent to xz. That's telling us that this length and this length are the same. Or on the main diagram, the two longest edges are congruent to each other. The second thing we are told is that wz is perpendicular to zy, and xy is perpendicular to zy. Well, normally we want to show that those two are perpendicular by making a right angle, right? I mean, that's what it means to be perpendicular, is that it makes right angles. So I'm showing the first perpendicular statement, wz is perpendicular to zy on both diagrams. And I'm showing the second statement on both diagrams, that xy is perpendicular to zy. The thing is, though, this does something really important for us. It means that we have two right angles that are congruent, or that are created. In other words, we find that angle z and angle y are right angles. I think that's going to be important to show that these are right triangles. So angle z and angle y are right angles. And again, that's because they're perpendicular. It's the definition of perpendicular lines. Mr. Strager, why'd you have to write it down in your proof? Well, it's because in order to use the hypotenuse leg theorem, it needs to be stated that these are right triangles. We can see that they're right triangles, but we need to demonstrate that fact. So the question is, how do we show that triangle WYZ and triangle XZY are right triangles? How do we show that? Well, that's literally what a right triangle is. It's a triangle that has a right angle. So in other words, it's really the definition of what a right triangle is. Because of the definition of a right triangle, it's a triangle with a right angle. These two are right triangles. Okay, so we know that these are right triangles, and we also know this longest length, the hypotenuse, is congruent to itself. So all we need to show is that one leg of each of these triangles is congruent to each other. And in fact, we see it from the main diagram. ZY and YZ are the same thing. They're reflexive. In other words, YZ in this first diagram and ZY in the second are the same line. That means they have to be congruent. So YZ is congruent to ZY by the reflexive property of congruence. That means that on both triangles, the hypotenuse and the leg are congruent. So we can say triangle WYZ is congruent to triangle XZY, and that's due to the hypotenuse leg congruency theorem. Done. Thank you so much, everybody. I hope you have a fantastic rest of your day.